by the power of good planning, after the talk on individual component verification in one spin, we now have a talk on using formal verification in safety verification from Tim Blackmore of Infineon. Tim manages a team responsible for CPU, IP, and subsystem verification, and has worked across all the usual verification methodologies, and in particular has been working in formal verification for over 13 years. So I'm going to hand over to Tim now.
So I think first thing to say about this talk is that it's very much reporting on work in progress. So what I'm not going to say is based on all our extensive experience, this is what you should be doing. It's just present some ideas and some early results. So a brief overview of what I cover in the talk. So I'll very briefly give an introduction to safety. So safety is a very large and quite technical subject, and I certainly can't do it any justice in 2 slides, but I'll just introduce the sort of concepts that we need during the rest of the presentation. And I do that in the context of automotive electronics, which is the bit I'm most familiar with. And the focus here will be on faults and on safety mechanisms. I'll then discuss a little bit, I'll discuss safety verification in general a little. So safety verification as opposed to functional verification, or it's different from functional verification. And then I'll move on to the use of the formal property checking tool. So start with safety. So I'll talk about safety in the context of the ISO 26262 standard, which concerns the prevention of electrical and electronic systems in vehicles from causing harm to people. So as Sergio mentioned, there's many safety standards. They've probably all got a lot in common, but my focus will be on the ISO 26262. Clearly, safety requirements of electronics in vehicles is increasing all the time. So already we have mechanical systems like braking and steering being replaced by wires and motors. There's things like airbags, which are electronically controlled, advanced driver automation systems, which typically increase the safety of a car, but if they go wrong, they do just the opposite. So if an airbag deploys while you're driving 70 miles an hour down the motorway, that car's not very safe. And then, of course, in 20 or 30 years' time, everyone's going to be being driven around in self-driving cars, and the safety implications there are huge. Electronic systems in cars usually involve a sensor to detect something that's going on, a controller to do some calculations. The sensor passes some data to the controller, which will carry out some calculations, and then I'll pass the results on to an actuator, which will respond somehow. And my focus here is on the controller, because we work on controllers. So here I'm only interested in technical safety, not in the process. So if you look at a standard like ISO 26262, then a lot of it will be concerned with process. I'm only going to talk about the technical aspects. And then going back to the notion of harm I introduced on the first sentence. So harm is usually caused by a failure, and that failure is usually triggered by a fault. So these are technical terms. And a fault may be systemic, as Sergio said, or it may be due to something like the degradation of your system over time, or it may be due to some transient happening like an alpha particle strike. So I think Sergio covered very well the sort of things you can do to avoid systemic faults during your development process. The focus here will be more on faults which occur during the lifetime of the product. And so what you need to be able to do is when your product is in the field and being used, you need to be able to detect when a fault occurs, and you need to be able to react to it. And in order to do this, there's many things you can do, but okay. And one of the things you can do is actually build in hardware safety mechanisms. So on your controller, you can add in some hardware safety mechanisms to detect when a part of your controller has gone wrong or has a fault during its lifetime. So the sort of hardware safety mechanisms you might use are things like lockstep CPUs. So you run the same calculations on 2 CPUs together. You have a comparator, and if there's a difference between the two, something has gone wrong. You might use error detection codes, as Sergio mentioned, so you might protect your data paths across a bus or your data in memory using error detection codes. You can use things like monitors, so you can have a hardware monitor monitoring your bus protocol. And again, if it sees a if it sees your bus protocol being breached somehow, then it can trigger a fault. Or you might have something like a timer. So you might expect your software to periodically update a timer. If that timer doesn't get updated, then you might have a live lock, deadlock situation. Anyway, something's gone wrong, and you can trigger. You can raise the safety alarm. Okay, so very brief introduction to safety. So I'm now going to move on to safety verification. So the goal of safety verification is to quantify the effectiveness of safety mechanisms in detecting unsafe faults. So during functional verification, you'll show that safety mechanisms work. So you'll show that your ECEC algorithm detects single faults, and using a formal tool, you can do that in a couple of hours. You don't have to show it's wired incorrectly, but you can actually show the algorithm works okay. You can show that if a fault propagates to the outputs of your CPU, then your lockstep comparator will raise an error. So this is the sort of things you do in functional verification. In safety verification, you're interested in how many faults actually propagate to the outputs of your CPU. So how many faults inside your CPU actually propagate to a safety mechanism? How many can you detect? So it's a quantification process. The way you quantify it is through something called diagnostic coverage, and this simply measures the percentage of faults that can lead to a failure that can be detected by a safety mechanism. There are lots of different kinds of possible faults. There's stuck-out faults, there's transient faults, there's bridged faults, there's more. A lot of this can be modeled by stuck-out faults, so I'll focus on stuck-out faults. Diagnostic coverage targets can be very high. If you want the highest levels of certification, so the ASIL D level of certification in the ISO 262, for instance, you might have to detect 99% or more, 99.9% maybe, of faults that occur inside your CPU. So very rigorous, very difficult to achieve. And as Sergio said, the ISO 262 standard mandates that this should be done on a netlist, not on RTL. So that's an extra complication. So you need to demonstrate a diagnostic coverage. So typically, how do you do this? Well, you might do this through fault simulations. Standard way to do this is through fault simulations. You just insert a fault, you run a set of stimuli, and you see whether the fault is detected by a safety mechanism. This sounds okay, but in practice this can be difficult. You need very high quality patterns. So if you have a fault deep down in your design, you need a pattern which is going to activate that fault and then propagate it, allow it to propagate to an output, or allow it to propagate to a safety mechanism. So these patterns, you can put a lot of work into generating them and writing them, and so it's good to get as much value from them as possible, and you can do things like use them for robustness validation, or you can, actually use them in something like safety software. So some software that you might run periodically on your chip to check that no faults have occurred in the chip. So that's another safety mechanism, a software safety mechanism rather than a hardware one. So the point is the patterns have value in themselves. So now I come on to safe faults. So some faults can never lead to a failure, and so they can cause harm, and these are called safe faults. So for instance, faults that cannot be activated in normal operation. So if you have a fault in your test or your debug logic, this is typically turned off during normal operation, and so faults in there typically aren't going to lead to any kind of failure which can cause harm. Another example is faults that cannot propagate off chip. If they can't affect the rest of the system, they can't cause any harm. So for instance, if you have a fault in your CPU that never makes it out of the CPU, then you're okay, that fault's safe. Another example is you might have whole blocks of logic which are inherently safe. So you might have a communication block on your controller which is only used in the infotainment system. And if it's properly isolated from the rest of the controller, you can regard all the faults in that logic as safe. So the point here is that safety mechanisms are not designed to detect safe faults. You don't want your safety mechanism to detect safe faults. You don't want your car going into limp home mode because the volume control on your radio isn't working. And so safe faults need to be excluded from measures of diagnostic coverage. because they artificially lower your results and they waste a lot of simulation time. So how to identify safe faults? Well, some are easy to identify. If you've got a whole communication block, in all of which the faults are safe, then that's quite easy to deal with. Some faults are very difficult to identify. So if you have a safe fault deep down in a lot of safety critical logic, you need some quite in-depth knowledge of your design in order to be able to identify that as safe. Our experience is this is very time consuming on RTL, and it's near impossible on gate level. So one possible solution is to use a formal property checking tool. So this introduces automation, and it has the added benefit of avoiding human error. So you don't get faults which are incorrectly identified as safe. So I move on to the use of the formal property checking tool in safety verification. Just a few notes on the scope of the work. So the work was carried out on the Tricol CPU. So the CPU is primarily used in automotive applications. It's used extensively in automotive applications. Last I heard, there was something like 150 million of them in cars around the world, and that number rising quickly, and a lot of them used in safety critical areas. So the aim of the work is to increase the diagnostic coverage, to give an accurate measure of diagnostic coverage, let's say, by identifying safe faults, formal identification of safe faults, and also by formal generation of patterns to activate and propagate some difficult faults. So these safe faults embedded down in some safety critical logic. The work, so when we're looking at these faults, we might generate many tens of thousands of properties. So clearly we don't handwrite them all. It's scripted, so the writing of the properties is scripted, the run of the properties is scripted, and the property sets can run overnight or even over days. So this slide doesn't say much. It's just saying that if you want to use a formal property checking tool to do, whether it's to do functional verification or safety verification or coverage closure or post-silicon debug or whatever, then you have to utilize the user interface to the tool. So you have to, and the user interface is primarily properties. So you have to write properties to describe what you're trying to do. You have to add constraints to these properties to describe the operating conditions, and then you might have some work on complexity issues, which might, for instance, change the way you compile the design into the tool or something. So the first strand of what we did was to try to formally identify faults that cannot be activated in normal operation. So a stockout fault on a signal or a net can only be activated when the signal takes the opposite value. So if your net is stuck to 0, then you're not going to be able to see that fault until that net should take the value 1. So a signal or a net that can take only one value cannot have the corresponding fault activated. So the properties are quite obvious here. So your properties are always your net is 0 or always your net is 1. And if one of these properties pass, then that fault can't be activated, so it's a safe fault. And the sort of constraints you apply are constraints to reflect normal operation mode. So you turn debug off, you turn test off, and such like. The properties are extremely simple, as you can see, and so they run very fast. And they can be run on RTL or they can be run at gate level. And so, for instance, we did a run of something like 100,000 faults, which took something like 60 license days on our cluster. And we did a smaller run on the netlist, which took maybe twice as long. So that's the first strand, faults that cannot be activated. The second one is faults that cannot be propagated. When you're talking about propagation of faults, you need an observation point. You need to look at somewhere that they might get propagated to. And then if the behavior of the design in the presence of the fault changes from the normal behavior of the design at the observation point, then the fault cannot be categorized as safe. It's led to a difference in behavior. The fault's led to a difference in behavior, so you cannot say it's safe. So the first question is, where should your observation points be? You can put them nice and close to your fault, and your properties will run quickly. But propagation is much more likely, so you're less likely to identify any, say, faults. Or you can put them a long way from your fault, nearer to your safety mechanisms, but then you're increasing your property complexity considerably, so you have much more logic to consider and over many more cycles. So there's somehow a trade-off here about where you should put your observation points. Next question is how to detect a change in design behavior. So perhaps the most obvious thing you can do is just take two instances of the design, put the fault in one, not in the other, and see if you get a difference in behavior between the two. That's fine, it does work, but again, because you have two instances of your design compiled into the tool, the complexity increases somewhat. So some initial work we've done on this is basically a proof of concept, let's say. So our goal was to formally identify that all the faults in the debug subblock of TriCore could not cause a failure. So we're hoping for something like near 100% identification of safe faults within the debug subblock. So we chose our initial observation points as the outputs of the subblock, because if the faults didn't show up there, then they weren't going to show up any further out. We ran the props at core level rather than at the subblock level, so not to artificially reduce the complexity, because we wanted to be able to demonstrate that we could do this at core level if need be. But instead of using two instances of the core, we found a set of constraints which put the debug subblock into its quiescent state. The idea was then for the property to insert, so we just take one copy of the design with these constraints, and the property inserts the fault and checks that the value on the output is equal to the value that we expect in the quiescent state. And the path indicates a safe fault. So we ran something over 1,100 of these properties, and only 20% of them passed. 70% were undecided, so we had banded fails or give-ups, banded passes or give-ups, and had about a 10% failure rate. Probably the vast majority of the undecided are likely to be passes, because the fails tend to happen quite quickly. And so we need to do some work here on the complexity. And the fails, some analysis of the fails suggested we had to move our observation points further out. Some of these faults would propagate outside of the block, but maybe not much further. Okay, so the third strand of what we did was to try to replace the fault simulations, which are extremely time-consuming and quite effort-intensive, with a formal property checker. So fault simulations require high-quantity stimuli, as I said, to activate and propagate the fault to a safety mechanism. You can try to generate random stimuli in order to do this, but ultimately, at some point, you're going to have to do some in-depth analysis of how some faults can be activated and propagated. So the benefit of using a formal property checking tool is you don't have to write any stimuli for it. So the property inserts a fault and checks whether a safety mechanism raises. A property can insert the fault and checks whether a safety mechanism raises an alarm. And if it does, then you know that the fault has been detected, and hence you can add that fault into your diagnostic coverage. You can put that one in the top of your ratio. But since the stimuli may be useful elsewhere, as I said earlier, an alternative is for the property to state that the safety mechanism does not raise an alarm. So you change the sense of the property, and now a failing property indicates the fault is successfully detected. And on top of this, you get a counterexample. So the tool will tell you the stimuli you need to apply in order to trigger the fault and propagate it to a safety mechanism. So we tried this out. So so some faults in some of the arithmetic logic of TriCore were very difficult to activate. They needed corner case values on the operands, which are difficult to determine, almost impossible to randomly generate. And using the approach outlined on the previous slide, we managed to generate the necessary operand values for 1,250 or thereabouts hard to activate faults. So we took two instances of the ALU block. In one instance, we inserted a fault by applying a cut and assuming that the net that was cut was stuck to 0 or 1. The property then states that the outputs of the two instances are the same. It fails. It gives us a counterexample in VTD format, and we have a script which would extract the necessary operands from the VTD, and then it's very easy to generate the test case to stimulate the fault. So this is actually very successful. Okay, so that's it. So conclusion. So formal property checking can be used to demonstrate faults are safe, so that they cannot lead to failures or harm, by identifying faults that cannot be activated, by identifying faults that cannot be propagated. It can also be used to give diagnostic coverage figures by proving faults or proving which faults raise a safety alarm. And as I've said, there may be complexity issues which need to be worked around. Yeah, that's it. Thank you.
Thanks, Tim. Thank you very much.
Sam Elliott from Imagination. I'm not particularly familiar with automotive safety type checks at all, but so the impression I get is that you pick a particular fault and then check a very specific fault, and then check whether that has any particular issues. Can you ask a tool to maybe identify a class of faults and prove that anything of this type would not cause a problem? So not necessarily this bit went wrong, but if any bit from this type was flipped, it wouldn't cause a problem.
So we're not doing very specific faults, we're doing very general faults. So yeah. So if you take the CPU and you need 99% fault coverage on your CPU, then you have to insert faults everywhere in your CPU and show that you detect 99% of them.
Sorry, yeah, I didn't mean that they weren't covering a wide range of things. I meant that for it's a given set of faults that you're introducing, and you check each individual one. Is that right? Or have I got that right?
Yeah, okay. Yeah. So you check them one by one. So you're saying, could you check families together?
Exactly.
Yes. You could. So the standard mandates that you have to demonstrate a certain coverage. So how you get there is sort of up to you. So if you can demonstrate that a certain family of faults somehow share some common behavior, which means that they are inherently safe, then that's fine. Yeah. But the standard does mandate that you need to demonstrate the diagnostic coverage.
In one of your slides, you were talking about using the equivalence checking method between two copies of the design, and you said that wasn't scaling very well, and so you used a single copy of the design and checked the fault against the quiescent value. Does that work for sequential designs, or is that a technique limited only to combination designs?
No, so this was a sequential design. So the complexity of propagation is always with sequential. It's always with register stages. So that's where the complexity comes in. So in fact, I wasn't talking about equivalence checking. I was talking about using a property checker to do it, having two instances compiled into a property checker. Okay. So doing it with an equivalence checker would be an alternative approach. But there were some of the faults were register stages away from the outputs of the block.
So for the case of the single instance where you are trying to detect if a fault causes a change in what I think you called the quiescent value of an output, what does that mean in the sequential design? What is the quiescent value?
Oh, so the question. So we determined what the quiescent values of the outputs were. So those were the outputs which meant that essentially
the non-fault case.
No, the quiescent state the state when the debug logic was at rest. Yeah, when it wasn't doing anything. So we demonstrated that under certain constraints, the logic wasn't having any impact on the rest of the design, and then we tried to show in the presence of a fault, it still had no impact on the rest of the design. And so we showed. So the property said essentially said always the outputs are always what we expect. Always the outputs are what we expect them to be. So there was no time boundedness in there at all. But we could deal with that because, let's say, the sequential depth wasn't very large. But as you start increasing the sequential depth of that design, then properties like that start becoming much more difficult to prove. Yeah.
Sorry, some supplemental on that. Were you only concerned with checking the case that the output of the debug logic was supposed to be quiescent?
Yeah. So we're interested in faults during normal operation, and so during normal operation, debug is turned off. So in the field, in the car, the chip doesn't have debug turned on. So that was the case we were interested in. Yeah.
Hi, Ashish from Imagination. Tim, you said in one case 1142 properties, 70% undecided. Did it have an impact on your overall coverage requirement?
Yeah. So this, like I said, these are early results. So this was, last time we did it, that's the results we got. Next time, that'll be better. But yeah. I mean, that's next to useless. Yeah, we need to get near 100% for that to be useful.
Yeah, I noticed in another slide you mentioned using invariants and so on. So I was just wondering if you tried any of that.
Yeah, not as yet. No. So I think invariants are a very good way to tackle complexity.
Martin Lampard from Jasper. Does the certification standard specify the fault models or the fault modes that you have to test for? You mentioned stuck at, but does it also have other modes?
So it does, yeah. So I think the requirements of stuck at are the highest. But yeah, so the transient faults you also have to do some of, and you could do transient faults in a similar way. Things like bridging faults are more difficult, but there are papers that suggest that you can still, some bridging faults can somehow be approximated by stuck-at faults and such like. So, yeah.
Is that all at the NELIS level?
Yeah, that's what the standard dictates, yeah. It's tough.
There's one question from the webinar, Tim, which says, did you think about using quantify or certitude for this type of fault detection mechanisms? This was, a lot of this had already been done, a lot of this was done in simulation, yeah. So tools like certitude are maybe useful there. Quantify, so what you don't have is a given property set. Your properties are actually aimed at saying, can I detect the fault? That's what your properties are saying. So rather than saying, is my fault detected by the property set, my properties are saying, is my fault detected by the hardware? So it's a different problem. So I think it's now time for, first of all, thank you very much, Tim. Thank you.